So good morning, guys. Today we're going to continue our discussion in flow past immersed objects, looking more specifically today at packed beds and fluidized beds. So a quick recap from Monday. We talked about drag force, and we also talked about terminal velocity. And for drag force, we identified that we can calculate the drag force for an object as a function of the drag coefficient, the fluid density, the fluid velocity squared, times our projected area divided by 2, or if we're looking for our drag coefficient, we can rearrange the expression like so, where we said that the drag coefficient is a function of our sphericity and our Reynolds number, given our sphericity is a function of our particle volume, the particle surface area, and the particle diameter or characteristic length. And we had a few rules of thumb for determining our drag coefficient based off Reynolds numbers. And we said for Reynolds numbers much less than 1, we can apply Stoke's law and say our drag coefficient is 24 with the Reynolds number, or if we want to solve directly for our drag force, due to it being viscous flow, we can solve for it by Stoke's law. For a transitional flow, with the Reynolds numbers existing between 1 and 1,000, our drag coefficient follows an exponential relationship, 18 minus Reynolds to the negative 0.6, and for turbulent flow with Reynolds numbers greater than 1,000, our drag coefficient approaches an average value. So depending on the system, we can solve for our Reynolds number, which is rho u naught diameter of P over mu, or G naught diameter of P over mu, identify our drag coefficient, and then solve for our drag force. We can apply the concept of drag force to solve for a terminal velocity of a falling object, or any object for that matter, where drag is involved. And we said for a typical object falling due to gravity, our drag force is approximately 4 times gravity times our characteristic length times the relative density between the object and the fluid over 3 times our drag coefficient times the density of the fluid. So that's the quick recap from Monday's lecture. Any questions on drag force or terminal velocity, or even the concepts that we had discussed in terms of the example problem? I don't know. Did we finish the example problem? I should probably take a look at that. Actually, we didn't finish the example problem. So we can go ahead and take another look at that one. And so just to kind of refresh your memory, the example we were looking at is this hot air balloon when it was essentially moving up due to a buoyant force. We know that the balloon has a diameter of 40 feet and a deflated mass of 50 pounds. And it's being released from air at 50 degrees Fahrenheit. So the question then becomes, what is the terminal velocity? where the forces acting upon the balloon are balanced and our acceleration of the balloon goes to 0. And for this system, we had our hot air balloon, where when we're considering the forces involved, we have a buoyant force, a force due to gravity, and a drag force. Which means if we're doing the solution, we can say the buoyant force is being matched and canceled out by the drag force and the force due to gravity. Now, based off what's given in the problem, we can solve for our buoyant force and our force due to gravity, but we can't directly solve for our drag force. And so we can say that the drag force involved is simply the buoyant force minus the force due to gravity. And so if we're wanting to solve for the force due to gravity, we can need the mass of our system times gravity, which for this hot air balloon, we know it has a deflated mass of 500 pounds. Plus, we need to know the density of the air in the balloon and the volume of the air in the balloon. Well, we can solve for the density of the air in the balloon. It's at 200 degrees Fahrenheit using the ideal gas equation. So I can say it is 14.7 psi times 29 pounds per pound mole over 10.73 psi cubic feet per pound mole Rankine times 660 Rankine, which gives us a density at 200 of approximately 0.06 pounds per cubic feet. With that in mind, I can then solve for the mass of the air in the balloon and say it is 0.06 pounds per cubic feet times pi times the volume or the diameter, which is 40 feet cubed, divided by 6. That will give us pound mass, and then to get it into pound force, I just multiply times gravity, 32.2 feet per second squared, and I divide by g sub c, or 32.2 pound mass feet per pound force second squared. And this gives me my force due to gravity and pound force units. And I find that this gravitational force is approximately 2,510. The next thing I need to do is solve for the buoyant force, which this system is essentially the volume of the air displaced, or the density of the air at 50 degrees times the volume of the balloon. So I need to know the density, the air at 50 degrees, which is once again using the ideal gas equation, 14.7 psi times 29 pounds per pound mole divided by 10.73 cubic feet psi per pound mole degree Rankine times 50 degrees, which is 510 degrees Rankine, which in this instance would be approximately 0.0779 pound mass per cubic feet. So the force due to gravity then, or the buoyant force, excuse me, should therefore be 0.0779 pound mass per cubic feet times the volume of the balloon, or pi times 40 feet cubed divided by 4, which equals approximately 2,610 pound force. Now, I also needed to multiply times G over G sub C to get it into pound force. So my buoyant force is 2,610 pound force. The force due to gravity is 2,510 pound force. That means my drag force is the difference between the two, which conveniently is simply 100 pound force. So with that in mind, knowing the drag force, I can then solve for my terminal velocity by using my drag force expression, where the velocity that I have is my terminal velocity. And rearranging this, I can say my terminal velocity is the square root of 2 times the drag force divided by the drag coefficient times the density times the projected area, or pi d squared over 4, which makes this an 8. So I can say my terminal velocity is 8 times 100 pound force. I need to convert that back into mass units. So 32.2 pound mass feet per pound force second squared divided by the drag coefficient, which was given as 0.6, divided by the density of the fluid. So in this case, it would be the colder fluid, or 0.0779 pound mass per cubic feet times pi times 40 feet squared. We do this, we should get a terminal velocity of approximately 8.8 feet per second. I can double check that really quickly.
Dr. Lopez,
Yes.
will you real quick just scroll up to your force of the gravity equation?
Yes. Hold on a second.
So in the force of gravity equation, you did the pi times 40 feet cubed over 6, but in the force of the buoyancy, you did pi 40 cubed over 4. Is there a reason for that?
Nah, it's a typo. It's over 6. Thank you. So let me double check this number. 8 times 100. Actually, when I do this, I get a little bit higher value. So I need to update my notes. I got about 10.5 feet per second. Any other questions on an example? Hold on. If not, then let's move on and start talking a little bit about flow through packed bed. So if I've got a packed bed in a system coming in at some pressure, leaving at another pressure, at some velocity, do I expect my pressure drop to be greater than or less than a typical flow through a pipe if the packed bed wasn't around?
Greater
That is correct. And so we can say the pressure drop will increase due to the obstructed flow. One thing that we can note is that the superficial velocity will increase through the packed bed. Even though our flow rate will remain constant. And so what that means is the fluid in the system, make it blue, it will come and approach the packed bed at some mean velocity u sub naught. As it moves through the packed bed, the presence of the bed itself causes the velocity of the fluid as it moves through to be greater than the velocity of the fluid outside of the packed bed. And this results with greater kinetic energy losses, frictional dissipation, and as we originally stated, an increase in our expected pressure drop. So I can ask, what factors will influence the pressure drop through our packed bed? What do you guys think?
Void fraction.
Void fraction, yes.
The length of the bed and the size of the particles.
So the bed length, particle size. What else?
The shape of the particles.
Yes.
viscosity.
Yeah, our fluid properties. Things like, our density, viscosity. That is correct. And so, if we're looking at this, a couple things we have to consider, which you've identified. When we're looking at particle size and shape, one thing that comes to mind is our particle sphericity. Keeping in mind, we stated that sphericity was 6 times the volume of the particle over the surface area and the diameter or characteristic length. One thing we also can consider is for a packed bed, we're interested in its effective diameter, which can be solved in terms of d sub e is equal to 4 times epsilon over AV times 1 minus epsilon, where epsilon is our void fraction. And this AV is just a ratio of the surface area of the particle over the volume of the particle, which is why sometimes you'll see this and some sphericity calculations. So if we apply our incompressible frictional flow expression to our packed bed system, take into account our changes in terms of effective diameter, we obtain the following expression that says the pressure drop through a packed bed could be summarized as 3 times our friction factor times our fluid density times our fluid velocity squared times length over our sphericity times our particle diameter or characteristic length times 1 minus epsilon over epsilon. And I'll pause for a second so you guys can update your notes.
Dr. Lopez, would that velocity be the velocity in the bed or in the pipe?
That's a very good question. This is the superficial velocity. So a lot of times you'll see it written as U sub naught.
Dr. Lopez, going back to your D sub E equation, it's 4 epsilon over A sub V times 1 minus epsilon or 1 minus another value.
No, that's 1 minus epsilon.
Thank you.
Of course. No problem. Now, one thing we can look at is if we rearrange this expression, I don't destroy my notes in the process, we can write an equation that looks like this. This would equal 3 times our friction factor. And what we find is at high Reynolds numbers, our friction factors can approach a fairly constant value. And for packed beds, a lot of this data says it converges such that 3 times our friction factor is empirically found to be 1.75. However, if we're not at high enough Reynolds numbers, we can consider a modification to the equation above, which accounts for laminar flow. And that modification would look like this, where I have delta P times V, diameter of the particle, times epsilon cubed over 1 minus epsilon times their density, velocity squared length equals 1.75 plus 150 over our Reynolds number, where this Reynolds number is calculated as our density times our superficial velocity times our particle diameter divided by 1 minus epsilon over viscosity. And so what we have, in a sense, is a dimensionalized or a dimensionless pressure drop as a function of turbulent flow and laminar flow.
Dr. Lopez,
Yes.
what is considered a high Reynolds number? Anything that's turbulent flow?
We're getting that. We'll get there in here in a second.
Okay, thank you.
Good question. Just give me 5 minutes and hopefully that question will be answered. And so, as nice as this dimensionless relationship is, at the end of the day, we often just want to know pressure drop, not some dimensionless pressure drop. And so, if we manipulate this equation back to solve for strictly the pressure drop, what we're left with is an equation that looks like this. And I'll actually put it in the form of F, which is just delta P over rho. And so what we get is 150 times U mu L times 1 minus epsilon squared divided by sphericity squared times rho times the diameter of the particle squared times epsilon cubed plus 1.75 times U naught squared L 1 minus epsilon divided by sphericity density. No, I don't need density. Particle epsilon cubed. Or this equation is important enough that I'll do my fancy circling. And this is what we typically call the Ergon equation. Now, you may or may not have seen this depending on the types of reaction systems you've been looking at. But when you're interested in solving for pressure drop, this is what we typically find. Now, you asked, okay, with the Ergon equation, we see we have two terms, right? Once again, we have our laminar flow and our turbulent flow. And the question then becomes, when can we assume something is laminar, when can we assume something's turbulent, and when something in between? Well, the good news is we do have some approximations that we can use, depending on if something is considered sufficiently laminar or sufficiently turbulent. So if our Reynolds number, here, let me double check my other notes, is about less than 10, we can rely on what's known as the Blake-Causany equation. which simplifies the Ergon equation to the first term. So we left with 150 times u mu naught L, 1 minus epsilon over sphericity squared, density, diameter of the particle squared, epsilon cubed. And so we can essentially neglect that second term. And if our Reynolds number is sufficiently high, or greater than 1,000, we can rely on the Burke-Plummer equation, or simplification, which simply states that our frictional dissipation is equal to a delta P over rho, which is equal to our 1.75 u naught squared L 1 minus epsilon over sphericity, diameter of the particle, epsilon cubed. And so these simplifications state for sufficiently laminar and sufficiently fully turbulent systems, we only have to consider one term in the Ergon equation.
Dr. Lopez, I have a question.
Go ahead.
So normally, like if we were applying this equation in reactors, we would kind of do it like in increments, and then our density would be the density corresponding to that increment. But if you were going to do it all in one shot like this, what density would you use, the inlet or the outlet?
You would typically want to use an arithmetic average.
Okay.
And so, go ahead.
Dr. Lopez, I got a question. So when we're looking at the Blake-Cosney equation,
Yes.
I see that the original Ergon equation had a square on that 1 minus epsilon term.
Oh, sorry.
Okay. Thanks.
I probably just wrote it. Sorry. Thank you for pointing that out. But yes, there should be a square there. All right. And if we're wanting to kind of develop a comparison between these expressions, you see this graph here, you'll see that dimensionless pressure drop term as a function of both the laminar and the turbulent contributions, where the Blake-Cosney values gives you this linear relationship. It's actually really not linear. It just looks like that because it's a log plot. But you can see essentially the Burke-Plummer approximation and the values it provides, as well as the Blake-Cosney and then the Burke-Plummer, as well as how the Ergon equation is able to describe flow at all Reynolds numbers. So is there any more questions on just kind of the concepts that I've introduced on packed beds, as well as the Ergon equation?
With you said the frictional factor, is that like the one from the Fanning chart?
Yes,
Okay.
that is correct. All right, so let's take a look at an example and see how well we can do. So let's say water at 30 degrees is passed through a chromatography column. I feel like I should change that. Packed with 50 micron spheres. The column is 5 millimeters in diameter with a packed length, or the bed length, of 1 meter. If the superficial velocity is 3 meters per hour, predict the pressure drop in pascals. All right, so let's jump back to our notes and see if we can set this up. So see, the example is going to be so we said the water was at 30 degrees. The diameter of the particles was 50 microns. It's 5 times 10 to the minus 5th meters. The diameter of the column was really small, 5 millimeters, which is 5 times 10 to the minus 3 meters. The bed length was 1 meters. The superficial velocity was 3 meters per hour, which is, if we want to make that meters per second, we shall get a fairly small value. 8.33 times 10 to the minus 4. And this didn't say anything about void fraction, so I'll assume my void fraction is 0.5. I'll say, and I'll make things simple in terms of viscosity, 10 to the minus 3 Pascal seconds, and a density of approximately 1,000 kilograms per cubic meter for the water. And so, with this in mind, we can consider the application of our Ergon expression, 150 u mu L times 1 minus epsilon squared divided by rho v squared diameter of the particle squared times epsilon cubed plus 1.75 u naught squared times L times 1 minus epsilon over v diameter of the particle epsilon cubed. And I'll say that phi is 1 because they're spheres. So here's a couple questions that I want you to think about and consider, because I'm going to shoot you all in the breakout rooms here in a second. So I want you to be able to solve each of these two terms in our Ergon equation. So when I send you off, I want you to work with your groups and find essentially what this number is and what this number is, so we can assess, is this laminar, turbulent, or transition? All right, so let me open up those rooms. So see if you can plug these values in and solve for each of those two terms. Your units should be in meters squared per second squared. All right, that should be enough time. All right, everybody, how did it go?
Pretty good.
Do we have an answer for each of these two terms?
For the first one, we got 100.
So about 100 meters squared per second squared. What about the second term?
I got about 0.01.
Got 0.01. Any other values?
I got 116 for that second value.
116.
I also got 0.01.
All right, well, let's take a look. So for this one, we have 1.75 times, what did I say, 8.33 times 10 to the minus 4 meters per second times 1 meter. The void fraction was 0.5, correct?
Velocity should be squared. Is that right?
Yes, it is. Divided by phi, which is 1. The diameter of the particle is 5 times 10 to the minus 5th meters, and 0.5 cubed. So let me throw this in my calculator really quick. So I do that calculation, I get about 0.097 meters squared per second squared. So yeah, right about 0.1. So in this case, if I had to ask if it's mainly laminar, turbulent, or transition, this fluid would fall into the laminar flow category. And you can kind of see that with that laminar flow expressional term being dominant in this calculation. And therefore, to solve for the pressure drop, I just take this 100.097 meters squared per second squared, and I multiply it times the density, 1,000 kilograms per cubic meter. And I'm left with about 100,000 pascals, or 100.1 kPa. Which means for that column and that bed, I lose almost an atmosphere's worth of pressure moving through that meter long column. I don't know why this is so messy. So any questions on that example? Any questions on packed beds, the use of the Ergon equation and how we have essentially two terms that make it up. Two terms that define the Ergon equation, one constituting pressional drop for laminar flow, and a second accounting for turbulent flow, which, depending on the flow situation, we can neglect and strictly using the Blake-Kozeny or the Burke-Plummer expression. All right, if not, then I think that's probably a great place to stop. And so on Friday, we'll consider the implications of fluidization and how our expressions for packed beds change when we essentially manipulate the system to make the bed a fluidized bed. But thank you guys for attending class. Take care, and I hope to see you in office hours or on Friday.
Thank you.
All right, take care.
Hey,
Hey, Dr.
I
Lopez.
have a question.
Go ahead.
Yes, go ahead.
Since we kind of have our design test, I'm kind of worried that I won't be able to check answers on the homework once I get a good start on it. Would you be willing to check answers over email?
Yeah,
over the
I've
weekend?
been checking answers over email. I'm just, if it's over the weekend, sometimes I'm a little delayed. So I would say try to get it to me like by the end of the day Saturday.
Okay. Thank you.
No problem.
Dr. Lopez.
Yes.
Last night I caught the end of your Zoom on the right at the end of the test. My phone I had my phone off during the test, and when I went to upload my PDF file, I couldn't get an email to send from my phone when I was trying to scan it. So it was about, I think it was like 5 or 6 minutes late. Is that okay?
Yeah, that's fine. I'm not going to be super strict on that I know people having issues.
Yeah, I know. It tried to send, and then of course, as soon as I got away of it, I stole somebody's phone. That way I could get it sent in from
I get that.
roommate, and then it finally sent about 30 minutes after. So
It's all right.
pretty hectic. So thank you so much for understanding.
No problem. Take care. Have a great day.
You too.